All right, well, let the party begin. So today we're going to introduce the concept of Fourier series, which you may be asking the question, how does that help me with circuit analysis and all the stuff we've been doing? Um, Fourier series is kind of an advanced topic. And the reason why it's a good topic for us to have or have a background on is primarily because as the world that we live in gets more and more nonlinear, and you can say, hey, wait a minute, how can we live in a nonlinear world? I'm talking about electric circuits. Like as we use more power electronics to kind of chop up waveforms and do different things, it's really helpful for us to understand how we can analyze these waveforms doing, whatever circuit analysis we've done so far. And so by doing Fourier series, we can convert some of these really ugly looking waveforms, and we can actually manage them and figure out, okay, well, this is just these frequencies that we need to look at. So then we can investigate them. They also have a tremendous amount of practical applications. When I was at the nuclear power plant, this is many years ago, over 30 years ago, one of the things that this guy, his name was Dana Fluid, he'd walk around with a little test set. And his job was to go around to all these like critical motors that had monitoring spots on them. And he'd put his probe on the motors and he would record whatever data was there. And the data they were collecting was vibrations on the motor. So then the motor data would be processed, and depending on what the Fourier series analysis performed, would tell you the bearing's starting to fail, the winding is starting to fail. It would give you a lot of information about it. And since these are really critical motors, like if they fail, you could potentially have a nuclear event of some sort. Then, they needed to make sure that they were right. So they were always doing preventive maintenance, including just seeing if there was going to be a problem. So they could actually take some proactive measurements to keep the motors from failing. So that's the one where it really started with Fourier series. We're going to see one here in a little bit, and hopefully it'll be kind of interesting and fun. But for most of you, you have no idea what I'm talking about, but that's okay. We'll make it work, because it wasn't that long ago that we had this technology. So what are we going to do? We're going to take periodic, and periodic means that they repeat over a certain time. And they're going to break them down or figure out how to break them down into their harmonics, meaning we're going to have integer multiples of this fundamental frequency, and we're going to go ahead and represent that. If you can identify if a function or a waveform is an even or an odd function, you can actually simplify the Fourier series analysis, because the Fourier series analysis can take a bit of work to get going. We're going to do what's called a spectrum plot, which you may or may not have already seen. So one of the things that a lot of the folks in senior projects like to do is they like to do total harmonic distortion. Well, doing total harmonic distortion is using some of the information that you get from the spectrum plot. We've already talked a little bit about some of the applications for Fourier series. So we'll actually put one out there this morning. And depending on the time, we'll be exposed to the Fourier transform. The only difference between a Fourier series and a Fourier transform is the waveform. If the waveform is periodic, you would use a Fourier series. If it's non-periodic, you use the Fourier transform, okay? And most of the time, when you get out in the real world, quote unquote, you assume that the waveform is it is non-periodic. And the reason being is because you can have a computer pretty quickly analyze and give you the power levels, and then you can look pretty quickly if it's likely to be a periodic waveform, or is it in fact a non-periodic. And so we'll take a look at that as we go, if this will go. All right. How many know what type of phone this is?
Touch tone.
Touch tone. This is a touch tone phone. And do any of you use a touch tone phone? Have you ever seen a touch tone phone? You might have had a touch tone phone in your house, maybe. And you may actually still have one, sort of. What I mean by that is, like, if you get your phone through Spectrum, like your internet service provider, your cable TV provider, that almost always is not a touch tone phone, but it tricks you a little bit to thinking it is touch tone. And even some of the touch tone phones that you're just using like a standard Verizon line, most of those have gone away from actual touch tone. They've switched to digital or voice over internet protocol, right? That's what VoIP stands for. And then the cell phone basically uses the same sort of concept. And what you're saying is, we're just going to go ahead and do everything digitally. But not too long ago, that was actually pretty complicated to have all these digital words and communication and be able to, get information going. Anybody here play Minecraft or saw the movie? What was weird about Minecraft, the game? Pixelated, kind of chunky and blocky, right? Not real smooth. And the reason being is because you needed to have 8-bit words because it just took so much memory or so much processing to be able to do it. It wasn't readily available. So 8-bit was not that uncommon because it was expensive to go. Now you've got 32 and 64. I mean, you can see stuff with computer games that almost look lifelike, right? But it wasn't that long ago. Like I said, when I was in grad school, so this is in the early 90s, I remember my supervisor said, here, you can use this computer. But the computer was really slow. And I ended up splurging on it was 4 megabytes of RAM, and it was $100.
Hey, do you mind if I share something with you real quick?
Sure, as long as you can share it with the whole class, because
Sure.
everybody's listening.
Oops, here you go.
Are you there?
Yeah.
Yeah, go ahead.
Well, look at the camera.
Oh, look at the camera. Okay,
Yeah,
sorry.
okay.
Oh, yeah.
Yeah,
Look at that.
yeah,
Everybody see what Arthur has there?
yeah, with the dial. It still works.
But is it actually plugged into anything?
Well, not at the moment.
Yeah, so I don't think you can actually plug rotary phones into the wall and they would work anymore.
I gave up the landline, but I did have one a few years ago. It still work.
The rotary phone worked?
Yep. Yeah,
Wow,
they
I'm
still
shocked.
where I live, they still supported pulse dialing.
Okay. So that's what the pulse dialing is. A rotary one would basically just pulse based on how far you rotated it. But most telephone systems ran away from that at least 20 years ago, maybe even longer.
When we were kids, we figured out that you could just toggle that switch on the handset and dial the number.
Just to make it more difficult. Yeah, because when you hung up the phone, there was a little lever or whatever that would indicate that you hung the phone up, and you could actually open, just pop it up and down, and you could get different things. So, but
That was a
now,
loop disconnect, they call that.
yeah.
Yeah.
But now everything is gone. That doesn't apply at all, right? Because
Nope.
you can just use internet. That's why everybody has long distance for free. Because why does it matter if a call is going from here to California or from here to VZ? It's still the same digital signal. It just has to go through different servers and all that stuff. But if you can get internet from here to California, you can certainly get voice over internet protocol and go ahead and do that. But why am I talking about this? Because here is the standard 12 button telephone for touchpad, right? You can actually get more, but this is the standard one. And so how did somebody know, or a computer or some other device know that you pressed a 6 or a 3? It has to be able to distinguish, right? Because dialing, 800 or 555, because nobody will get me in trouble. 1212 could be very different than 2121, right? Like you can get the wrong party. Well, what happens is that you actually, whenever you hit a key, you've got 2 frequencies that are combined and summed together. So literally you have 697 hertz that's constantly going out. There's just a bus bar that has a frequency of 697 hertz. Then you also have one at 770, 852, and 941. You also have another bus bar, if you will, that has 1209, 1336, and 1477. And when you press a button, whatever button you want, it's going to be the output that you send along the line is going to be the addition of those 2 waveforms. So they're just summed together at a location. So if you press 6, you're going to get 770 hertz, which is a perfect sine wave, plus 1477 hertz, which again is another perfect sine wave, and you are not going to get a perfect sine wave output. And so that's why when we talk about multiplexing, it's essentially addition of the frequencies that we have there. So it transmits the sound when you press the 5 or the 6 or whatever, it's an audible frequency. These are all audible. These are all things that you can hear. And so someone at the other end, or most likely a computer or some sort of device that could filter out, would be able to ascertain what that frequency or what those two frequencies were. But the multiplexing of the two signals looks like the top figure. Does that look like 770 hertz or 1,336 hertz? Doesn't look like it at all, does it? So if you're on the other end, how can you tell that somebody pressed 5, right? 770 and 1336. Well, what you would do at the other end is you would perform a Fourier series, and you would actually see in the output of the Fourier series, you have two big spikes, one at 770 and one at 1336. So I can't really tell just by looking at the top waveform that that's pressing number 5, but on the bottom, I can tell I pressed number 5 because I have a lot of power at 770 and a lot at 1336, but no power essentially anyplace else. All right. So you perform the Fourier series, and then you can tell. I brought this up just for fun. I think Arthur was already doing it. So this is just this online tone generator. So can you tell me if you can hear this in audio land? TV land, can you hear that?
No, I can't, but it's funny. That's the same one I pulled up.
Oh, you did? Okay. Yeah, it's an easy one to find. But a 1, if I hit it, has got 2 low frequencies. If I go to D, much higher tone, right? Much higher pitch. So let's go from a 1 to a 2. I wish this would stop doing this. Not a huge difference, but a subtle difference. How about 1 to 2 or 1 to 4? All right, I need all of you to, I need volunteers. Close your eyes. I'm going to hit a button. Tell me which number I hit, right? What number was it? No way of knowing what it is, right? If you watch old TV shows, there was a Seinfeld episode where Kramer actually was going to do a landline where he had a business where he would give you movie reviews. And then they had touch tone phone, and he was listening in, and it was like, okay, press 1 if you want, I don't know, Silence of the Lambs. Press 2 if you want The Money Pit, whatever. And then they would hit the button, and you'd see him pause because he couldn't tell the difference between 1 or a 2. But then he would say, okay, well, please tell me which number. I can't determine. So please tell me which, say which movie you want to have a review on. And he ended up having to go with that. But with computers, I can do this no problem. I can hear it, but I can't distinguish what's a 1 or a 4. Maybe if somebody spent all day training or days and days and days to be able to decipher it, they might be able to do it. But with the Fourier series, I don't even have to know what it sounds like. I'll actually look at the power levels. Okay.
What was really funny about that too is that the equipment could decode that faster than you could press and release that key.
Yes. Because this is going in at 770 hertz, which means it changes, goes through one complete cycle in 1 over 770 seconds, right? So 1 over 770. So what is that, like a megahertz frequency? So it can, or not micro, it would be like microseconds of time.
1.3 milliseconds.
1.3 milliseconds, yeah. So very, very fast. You know what the signal is. It would be able to decipher it immediately. That's why when you hit the buttons, it could do it really quickly. Okay. But again, this is old technology. Not that long ago, though, right? Some of you all said that you actually did it. You had a touch tone phone. But here's the thing. You're all being tricked. Because if you have your cell phone and you hit buttons, it just provides the audio feedback. it sounds like a 1 or a 5 or an 8 used to sound like with the touch tone. When you hit a button now, all it does is it shows you on your screen what number you pressed, and it tries to provide you some sort of audio feedback. It's like go to an elevator and hit the up or down button. If the light doesn't go on, what do?
Press it again.
You press it, 50 times until you're like, okay, maybe the light's off, right? You just assume it's broken. So if you didn't have some sort of feedback that the number you pressed was identified by the phone, it would burp at you. And so wouldn't the perfect feedback be, 20 years ago or 15 years ago, whatever they started to transition to VoIP, why not make it sound the same as what we used to sound like? It's just literally a wave file that they play. So when you press 2, if you hear the feedback, all it does is play a wave file. I have a Pixel that runs the latest version of Android.
Yep.
And it's not the latest Pixel. It's just the latest version of Android because Google committed that they would update that from Pixel 8 on. They would keep the OS updated. Mine, I don't know what version of OS it has, but now when you hit a button, you just hear like a bing, and then you have a little bit of a vibration, like a feedback that's on your finger. So I don't even know if this is going to be doing this anymore, right? Meaning, are they even going to play signal? Does anybody's cell phone, when you push the button, does it sound like the old touch tone? Did you set it up that way, or just your phone is old enough, maybe they hadn't transitioned over, or does it?
Mine used to, but
Yeah. Yeah, they figured something that was 10 or 15 or 20 years ago. Some of the people who have cell phones have no idea what those noises are or how they used to dial. But that's how they used to do it. Now, like I said, there's no real reason to do it. But you can still, as you can see, you can still find those. And if you go to developing countries, you'll actually see that they still use dial tone because that equipment is so easy to work with. It's bulletproof. You don't have a server down in wherever and then knock out everybody's phone. It's just very reliable. Telephone signals used to be extremely reliable. Now, if your internet's out, you don't have any calls, right? And I wonder, and I don't know if the answer to the question is Arthur might be able to figure this out, but everybody knows at your house, if you have a landline going into your house, by law, that line has to be energized. And if you dial 911, that will go automatically to dispatch. There's no charge to you. If you look at your cell phone bill, there's a 911 fee, which is the fee that we all pay so that 911 system will be active for anybody. So if you go to a phone, even if you're not paying for a service, if you pick it up and dial 911, it will call. It will make the call. And so I wonder if the 911 systems, because they're older and basic, do they still use a touch tone system? There's no reason to upgrade it, right? It's literally just to call an emergency number, and it's only going to be 3 digits. So why do that? I don't know. I'm not exactly sure. I would imagine it's what's that?
I can find out. I had to go to the town hall next week to register the car. I can pop downstairs and ask them.
Yeah, I wonder, like, because most of the systems have switched over to digital. Like,
Yeah.
even when you make a call, a regular call, it has to be done digitally. But with 911, it's different because it's considered an emergency. So it can't fail because of a server error or something like that. It's got to be reliable. So you have this old technology that's bulletproof. So why not continue to use it? So your cell phone is a radio. That's all it is. It's a two-way radio, transmits and receives. You can call it something else, but it literally is a radio because it wirelessly transmits. It transmits a lot of data, right? It does it digitally, but in reality, it's just a radio. And so all the signals that you get back and forth, you used to be able to transmit things analog. It wasn't that long ago that cable TV was transmitted via analog. You used to go online. I never did this, I swear, but you used to go online and people would sell cable converter boxes where you could steal cable TV. I don't know how long ago that was. I actually never did that because I'm not a big TV watcher, but you could get, I don't know, boxes or whatever, and you could get whatever, Disney, ESPN, I don't know, pick a channel that you like to watch, and you didn't have to have a service, and you can actually get it for free because the old systems, the way that it worked is they had these channels that were being sent out, and they always had all the channels that would go through. Then at your box, there would be a filter in there so that when you depress the channel, the filter would enable the signal to pass so you could actually watch it on your TV. Now, that doesn't matter because everything's digital. So you're actually passing information back and forth. I want to watch this channel and I want to do this. That's why you can actually watch movies, right? You can watch a movie from your house. You can press play, you can press pause, you can go to a different movie. Not everybody else is at the same point in the movie that you are, but you're able to actually view the movie because of that technology. So everything pretty much is digital because you can pack in a lot more information. It used to be, and I don't know if it still is the case, but it used to be that you can get analog radio over the airwaves, like FM stations. I don't know. I like to listen to 89.3. Anybody know what that station is?
Yep.
I'm old, so people, I like more alternative rock. So I like WHSN out of Husson that has, that's like really the only alternative rock station in this area. Their signal is really weak, so you probably don't get it all that well if you're in Orono. But all that stuff is transmitted to digital because you can have like 2 or 3 different audio channels on a digital channel in one frequency range. It still transmits over 89.3 megahertz, but it's all transmitted digitally. So you can put a lot more information than it used to be. So now if you have anybody here, like my car is from 2012, but I have a radio that if it has a digital channel, it'll actually tell me the name of the song and the artist.
Oh.
Right?
Oh, yeah.
Back in the day.
yes.
What's that?
Radio data system. That actually was analog. That actually was analog when it first came out. That was 96, 97, I think, when that first emerged.
So when they actually would tell you the name of the song and this,
Yeah.
Okay.
Yeah, yeah, that was
digital.
that was a GM Bose thing.
Okay. Yeah. So that was additional information, but now it all comes across digitally and they just provide the information. That's why they call it HD audio, right? It's high definition. It's better quality sound, which is funny because people love to buy old vinyl, play records, and they say, oh, the sound is impeccable. But then on your car, oh, if you want HD, you got to have it all digital, which it kind of is in the opposite direction of things. So
I think that's more for the convenience. I mean, I have to fully disclose that I have a big bookcase of vinyl records sitting in the living room.
yeah, but there are some people who claim that vinyl is an actual better sound than digital, allegedly.
I mean, they're in good condition and I play them and I can't really tell the difference. I wouldn't say one's better than the other.
Okay. I think if you're talking to the high-end audio enthusiast, not somebody who likes to drive around in an old Volkswagen Beetle, no offense, but they're driving around in Maybachs, you know what I mean? Like $4 million cars or whatever. They want super duper high-end stuff. So they want like a vinyl record player that's probably $50,000.
Well, let's see. I have a linear tracking turntable, which is kind of not common.
Yeah.
My daily driver car is a Bose audio system, which is not exactly, junk.
Yeah.
But
I'm just teasing you out there.
For
like
me,
if you
it's the portability. For me, it's the portability with having, the audio on the go, because FM radio, let's be honest, it's nothing but ads.
Well, so isn't streaming podcasts unless you pay for a service.
No, they had me hostage on that one. I pay.
Okay, there you go. But you see the idea, right? Like technology, there's sometimes everybody likes to move forward, but there are things that people cling and hold on to, like the dial tone on your phone.
Yep.
I mean, it's laughable, but if it's been digital and you hear the button number you pressed and it's the old dial tone, why would you need the old dial tone? That's not what the phone, that's just a harking back to maybe when you were younger, like, oh, I remember when we had a dial tone. But a lot of that stuff is just, it's disappearing. It's going away.
Well, what'll really get your attention is you can find all the videos on YouTube that the Bell system put out in the 50s when not dial tone, but when actually dialing the phone, when they did away with operators and switchboards.
Yep.
Dial numbers coming to your town. And you look at that and you're like, oh, how quaint, but it's like, no, that was a big deal.
Oh yeah, it was huge. So it used to be that you had operators with huge patch panels and they would literally connect people with different wires. And so you would pick up the phone. There was no, you would rotate a crank just to let people know, hey, I want to make some calls. And then they would pick it up on the other end and they say, who do you want to call? And I want to call Mary Jo down the street. And then they would connect your line over to Mary Jo's line. They would do it manually. But those have gone away. What's that?
Provided there was nobody else on the line.
Provided there was nobody else on the line, yeah.
Yeah.
But they did have the capability, if you said it was an emergency, they would break in, they would cut in and do that. And you can still do that today. If it's an emergency, you can call the operator and say, I have an emergency, I need you to cut into the line, and you can actually interrupt that. But that was way even before me. I don't remember that. But you used to have the pulsing one where you would rotate, and you saw the rotary phone that Arthur put up. That one was a rotational one. And what you saw there is it would pulse. Like you would do one, it would pulse once. Two, it would pulse twice. And you would rotate the phone around to the positions so that you would get the right number. But those were always making mistakes, because if you didn't rotate all the way through, like if you got lazy, if your finger slipped out, instead of a 4, you dial a 3, or instead of a 7, you might dial a 5, just because you didn't go. So that there was the only feedback you had was a pulsing, and nobody paid attention to how many times it pulsed. You just went ahead with that. But I don't think anybody does rotary phones. The last one I think was in Maine that did it, but that was 15 or 20 years ago. Actually, an alumni, he ran the telephone system that used that, which he no longer uses. So anyway, that's why I have this, which is you can go back old school and take a look at how all this stuff works. Because it's kind of interesting to see how the technology has evolved. And it also might influence a little bit of how the technology will move forward, right? Now, obviously, we've done everything with computers, and we use digital I/O, but now they're talking about quarks, and would we be able to move more data with less power? You know, that's kind of moving forward. We don't get stuck in the past. We try to improve things, but is it really any better? Who knows? Like now there's what, 1,000 channels on TV? How often do you all spend searching around on YouTube looking for something to entertain your brain, as opposed to finding a station? When you had 3 TV stations back in the day, you're like, well, I better learn to like this particular program. And the benefit of that is they actually spent a lot of time and effort to make their programs quality, because they know they only had 3 and they were competing against 2 other ones. Now it's like you got to compete against Amazon Prime and Hulu and some of the stuff that they put out there. You're like, wow, this is not like, my kids like to watch animated stuff, and some of the Netflix ones that they have, it's like, boy, oh boy, this is a stinker of a movie. But the kids got, liked it, but they made the movie for $10,000 or whatever. They don't have to compete.
Here we go.
There we go. Yes. Get into some math. Enough talking, enough blabbing about stuff. So how do we do a Fourier series? So a periodic waveform means it has a certain amount of time when the waveform will repeat. Okay. The exact replica of the waveform. So it has to be repeating for Fourier series to be able to do that. And so our period T is 2 times pi divided by omega naught. We're not using frequency here. We're going to use omegas, because we're going to be doing a lot of sines and cosines. So you can get the terms, you can see the representation here. And so now we have the first harmonic, which is really called the fundamental frequency. And I think I'm missing let me fix this real quick. Let's change this to N.
Yeah, okay.
Makes it look a little bit better.
That did. Something didn't look quite right. I'm like, wait a minute. I was like, oh, that's it.
Oops.
Yeah.
All right, so the fundamental frequency is the lowest frequency of the periodic waveform, which means however long it takes, how much time it takes, that initial period to go ahead and that waveform repeats, that's the fundamental frequency. That is n equal to 1, because n is an integer, okay? It's a multiplier times the fundamental frequency, or in this case, we have omega sub 0, okay? So the first harmonic is the same thing as the fundamental, and you just substitute n equals 1. So you have a cosine waveform that is going to be rotating at the same frequency, or takes the same amount of time that the fundamental one, or how long the waveform goes. Now, because it is a periodic signal, you only are going to add in integer multiples of the fundamental to rebuild your waveform. That's the thing about doing Fourier series. You're adding in a bunch of either sines, cosines, or sometimes both, depending how you look at it. You're adding those together to replicate your initial waveform. Okay? And why do I want to do sines and cosines? because sines and cosines are easy to analyze, right? We could do steady state circuit analysis if we wanted to. We could do Laplace if we wanted to see what's going on, but we don't have a choppy waveform that is very difficult to analyze. So if it's Fourier, it's always going to be integer multiples, n equals 1, 2, 3, 4, 5, 6, 7, 8, all the way up until you get to infinity. And that's where it gets a little wonky. To replicate a Fourier series, you actually have to go all the way out till n equals infinity. So you would have an infinite number of harmonics to do it. Now, you don't often do that because usually the first 5, maybe 10 harmonics are enough to get a pretty darn close approximation to the original waveform. But that's how we get this particular one. So if we wanted to build a voltage, we would have a voltage, and this, again, this is in time domain. We take the cosine at the fundamental, then we add on the second harmonic, which is twice the frequency, third harmonic, which is 3 times the frequency, and on and on and on. There is going to be an amplitude associated with those, and the amplitude is going to change based on which harmonic you're looking at. So how do you determine if a function is periodic? Well, if you have any place in time, could be 1 second, 1 million seconds, it doesn't matter. Any place you're looking at, if you add the period to it, which is the fundamental frequency, if you add that period to it, you will get the exact same original function that is in the time domain, right? So it doesn't matter as long as you add on period. You can pick any time. Like I said, 1 second, 1,000 seconds, 1 million seconds. You're always going to get that same value, whether it's 1,000 seconds or 1 million seconds. It doesn't matter. You just go ahead and add the period to it, and it's going to replicate. So here's an easy waveform. Let me get this out of the way. Here's a sine wave. And the period is equal to 2 times pi. Because a sine wave starts and ends and then restarts. If it's periodic, it has to restart. It has to restart at 2 times pi. Okay? So it's repeating every 2 pi radians. Not radians, seconds. I said radians, but this is actually has the unit in seconds because this x-axis is in seconds, right? Make sense? What's the frequency of this? Well, my period is equal to 1 over my frequency. So my frequency is equal to 1 over my period. That's 1 over 2 pi, and this is in hertz. If I want to know what omega is equal to 2 pi times f. That frequency is 1 radian per second, right? So this has a fundamental frequency. This sine wave has a fundamental frequency of 1 radian per second. Is there anything else on the slide that'll tell you what the period is? No, don't look at the graph. Is there anything here that'll tell you what the sine wave is? I mean, what the period is. Not including the graph.
Well, if you know the frequency, you can find it.
But let's say I'm trying to figure out the frequency.
Oh, yeah.
Is there anything on this that actually tells me what the frequency is?
The time that's elapsed.
No, we can't look at the graph.
True.
It's yelling at you. It's screaming at you.
Oh, yeah. It's how many radians per second.
Right here, right?
Mm-hmm.
The sine of x, we'll put it as the sine of t, is equal to the sine of omega t. What does omega equal?
2 times pi times the frequency.
But isn't that omega equals 1? If it's just equal to t, right? Omega is equal to 1 radian per second. So this right here told you what the frequency was in radians per second. because it was just a sine of x or the sine of t. There was no multiplier up front there. If it's a sine of 10x or 20x or 1000x, then you would know that omega is not equal to 1, right? It's equal to 2 or 10 or 1000, doesn't necessarily matter. So then we can check it and we can see any place along here. Let's pick this point. If we go 2 pi away, what do you know? We're at the same value. If we pick something over here, actually, let's get it right at 4. If I go all the way over to here, or 2 pi later, you end up with the exact same point. All right? Make sense? So be careful because omega is radians per second, but the period is 1 over omega. So that's where it gets to be a little bit confusing, right? When you're trying to do these calculations. So just be mindful that you understand what's going on, okay? And I tried to put this up here to show you, because it is a bit confusing. How do you get t? You don't get t directly from omega, right? You get it from 1 over the frequency, and then the frequency is equal to omega divided by 2 pi. That's where we get the 2 pi introduction here. Does that make sense? Because it's a little weird when you start saying, how did you get 2 pi from, you know, that sine of x equation? Well, when I walk through and I show the t and then omega, hopefully that makes sense. Does that make sense? Kind of, sort of, maybe. Okay, so if we just kept continuing it, right, which it should, a sine wave is going to continue for forever as long as you keep it energized, then our system or our waveform is in fact periodic. And so now our fundamental frequency, omega naught, is equal to 1 radians per second. So every additional sine and or cosine that is on there is going to have a frequency that is an integer multiple of 2 times pi. It'll be 2 pi, 4 pi, 2 pi, 4 pi, 6 pi, 8 pi, on and on and on and on as we go. All right, that's the thing about the fundamental. Here's another example. This one is not as obvious. So we've got a function, we'll call it h. And that's going to be equal to a times the cosine of x plus b times the sine of x. Now, if we want to go in and add our period, right, which we're going to say is 2 pi, we're going to go and add in x plus 2 pi everywhere we see x. And then we end up with a cosine x plus 2 pi plus b sine x plus 2 pi, right? 2 pi is a rotation of 360 degrees, which means not only the sine wave, but the cosine wave starts to repeat after every 360 degrees. So we can basically throw those out, right? When we add or subtract 360 degrees, we can just remove those because that's adding or subtracting 0, isn't it? It's the same thing. So we go back to our original expression, which means that h of x plus 2 pi is equal to h of x. So this is a periodic function. How about another one? Let's go just the cosine of x. Our function is just a cosine of x. So now we're going to go in and we're going to add plus pi. So we see that h of x plus pi is equal to, again, the cosine of x plus h, which is equal to x of negative x. And then we add in 2 pi, and we end up getting h of x. So is this one periodic? Kind of throwing you for a loop here, because this one says h of x is equal to h of minus x. So is it periodic? It is, because remember what I said, for a base sine or cosine, we know that the period is 2 pi. We only added a 1 pi in here. We didn't add 2 times pi, we added 1. So we did not add in the actual period. We didn't check here should be 2t. We actually plugged in t over 2. So that is not a way to check to see if it's periodic. It is something really useful, though. It tells us that whenever you plug in a value of x and you're essentially a mirror image from the point on this x-axis, so you're basically flipping the x-axis over, you end up with minus x. So if I plug in h of 1, okay, then that would be equal to h of minus 1. And if you give me a few minutes, we'll actually see that that's a very, very, very helpful feature that we'll get. All right, here's another example. Periodic signal has a 2 millisecond period. The net positive area over one cycle appears to be greater than the net negative area. List the 5 lowest frequencies that would probably, not guaranteed, but would probably appear if we were to do a spectrum plot. And all a spectrum plot is you have DC, you have the fundamental, you have 2 times the fundamental, 3 times the fundamental, and on and on and on and on. So the first thing we're going to do is tease out, does this description that we have here make sense? Well, we have a 2 millisecond period, so I know what t is equal to. It's 2 milliseconds, right? That's the first thing I'm going to write down. What does the next sentence tell us about the waveform? What's that? Yeah, if you want to draw a picture, and let's just do something that looks like this. Assuming all those humps are the same, but I know they don't look anywhere near it, but that's the best artistry that I can do. Looking at this waveform, does that tell you something? Remember, we're going to actually be able to replicate this waveform by adding a bunch of sines and cosines together. There's one part of this waveform that we can't recreate by adding a bunch of sines and or cosines together. What is that? Andrew kind of sort of said it. No, not the frequency. Say more. Yeah. Doesn't this have to have an average value that is above 0? It's got a DC offset, right? So if you have a waveform that is not centered about the x-axis, meaning the area above is equal to the area below, then you have to have a DC offset. So when we talk about replacing a periodic signal that is DC offset, right, is above or below the x-axis, it doesn't need to be above, it can be below, then we've got to go ahead and add a DC offset. We cannot create a DC signal with adding a bunch of sines and cosines together. It's impossible. Because the sines and the cosines, the area will cancel out, right? If it's a pure sine wave or a pure cosine wave, the area above is always going to match the area below. So when you add all those up forever, the average over one cycle is 0. You can add a bazillion zeros together and you're still not going to get anything but 0. So the very lowest one that I'm going to have is DC, right? If you would consider that a frequency, but that has omega equal to 0. What would be the next lowest frequency that you would have or that you would find? Any ideas? The first point of the offset? What do you mean?
So the dotted line, the first point that we find on the dotted line going down on your feet.
Well, what I'm looking for is frequencies, right? I'm actually looking for the frequencies of the harmonic signals. So what would be the next most likely frequency? Very good. What's the fundamental frequency? 1/2 milliseconds, which is equal to 500 hertz, I believe. So the next most likely one I would have, the frequency would be equal to 500 hertz. What would be my next one? After 500 hertz.
1,000 hertz.
Yeah, because this is the fundamental. So to get F here, I took F naught and multiplied it by 1. Over here, I'm going to do F naught and multiply it by an integer multiple. The next integer that I can get to that's positive is 2. So F becomes 1,000 hertz or 1 kilohertz. How about next one?
1.5 kilohertz.
Multiply by 3. So F equals 1.5 kilohertz. And last,
sorry, 2 kilohertz, right?
right, 2.0 kilohertz. So if there's any contributions at all, these are the next 5. If you want to add one more, the 2.5, that's 5. These would be the next ones that you would actually see power level at. Okay. You won't see anything at 750 or 1250 or 1800 because again, this is periodic. So there is no contribution from anything but integer multiples of the fundamental. So there's our frequencies, including DC. Right? Questions on that? DC just means an average value. There's no frequency. The frequency is 0. So it's a constant. It doesn't drop below, right? It's not a waveform at all. It's just a constant DC. It's like a unit step. Okay. All right, so now now we get a little bit of understanding, or hopefully have a little bit of understanding of how we actually can build these functions. Let's take our next step and figure out how to simplify some of the math. We're going to do this up front, and then towards the end, we'll give you a table where hopefully it'll make it a little easier to represent these. So the first thing we're going to do is define what an even function is. An even function is whenever you plug in a positive value of x. So you're in the time domain on the positive side. If it's periodic, you're just assuming that waveform goes on forever, including a negative forever. So the positive value of x is going to give you the same result as plugging in the negative value of x. So let's take a look at this one. F of x equals minus 3x squared plus 4. We're going to assume that that's periodic. So the first thing we're going to do is try x equal 2. So let's just plug in numbers. F of 2 equals 3 times 2 squared plus 4. 2 squared is equal to 4. 4 times negative 3 is negative 12. Plus 4 is negative 8. Now I'm going to go in and do a negative 2, right? Because I've got to plug in the negative value or the negative time. And so if I plug in negative 2, I get negative 3 times negative 2 squared, which again is 4. 4 times negative 3, negative 12, plus 4 is negative 8. So this is an even function. These are giving you the same value. They're both equaling negative 8. That's an even function. If it's an odd function, then f of minus x is going to almost be the same of f of x, but it's going to be equal to the negative of f of x. So let's plug in an example. Let's do f of x equals 2x cubed minus 4x. Plug in 2 again. That worked before. Let's do it again. So f of 2 is equal to 2 times 2 cubed, which is equal to 2 times 8, which is 16, minus 4 times 2. So minus 4 times 2 is 8. So 16 minus 8 is equal to positive 8. I'm going to do the same thing now and evaluate at negative 2. So f of -2 is going to be equal to 2 times -2 cubed. -2 cubed is -8. So 12 times -8 is equal to -16. Now I'm going to go ahead and subtract -4 times -2. So -16 times minus +8. Sorry, -16 plus 8, right? Because negative and negative become positive. So -16 plus 8 becomes -8. You will notice these are opposite. This is a negative function. Let's jump back up here. Look at this equation over here. Note it. Look at this equation over here. Is there any clue, any hint as to possibly how you can figure out if it's a positive or an even or an odd function? Luke. Yeah. Look at the exponents. I have an x squared. X to the 2 means x is raised to an even power, right? And there is no other x term here, but you could call it x to the 0. What about over here? X cubed, x is raised to an odd power. X here is raised to the 1. That's an odd power. So the concept for even and odd functions come from if you have squared or cubes. This is only a very limited case because none of our functions are actually going to look like this. They're going to look a lot different. But that's where the term even and odd functions came from. Because it's like, why would f of x equal to f of minus x? Why would they say that that's even? Doesn't make any sense, right? Or why would f of x equal minus f of minus x? Why would that be an odd function? It's a negative, but it's not odd. It's not like an odd number like a 3 or 6 or 7, but it's because if you raise it to those exponents, that's what you would have.
Aren't odd functions also reflected about the line y equals x?
Line y equals x? No.
No, okay.
It'd be y. It's mirrored. Well, let me back up. So if it's an odd function, yes, it would be, let me back up and make sure I'm saying this. It's not just x, because we'll see. Well, let's look at, I've got a couple of them, and then we can actually look at one that we'll see. Okay.
So I know if it's even, it's reflected about,
it's reflected about the y-axis.
The y-axis, yeah.
But I'd have to take a look at it, because when you say reflected about the y, I just think that it's copied down. And it's also copied down.
No, the line y equals, in other words, it's reflected across the diagonal line of y equals x.
Yes. I think it also, because if you wanted this to be an odd function, this would kind of have to do this, right?
Yeah.
So it's not just reflected across the x-axis, because if you wanted to do that,
no,
then it would do something like that, right?
Yeah, it's reflected across both, if I remember right.
It's reflected across both. Yeah, that's why I was struggling to answer your question. It's not just one axis. It would be reflected across both.
Yeah, but the line y equals x is the diagonal line that it basically, if you graph that line, if you grafted y equals x and then an odd function, and you would see that it's reflected about.
Well, I don't know, because here is y equals x, right? You can see, and that doesn't look like it's reflecting anything, does it?
No, because that's an even function.
Right. Well, we'll try that on the next one. We'll see.
Yeah.
See how that goes. But these two are even functions, right? Because here is here, and here is here, right? They're the exact same point. There is no negative value. Same thing over here, right? That one's just more screaming at you that it is in fact an even function. Let's go over here. These are odd functions, and we'll try to do what Arthur just suggested. So this is an odd function because over here is opposite, right?
Mm-hmm.
Over here is opposite. Over here is over here. Now, if we did our diagonal line as Arthur suggested, let's see if I can do this at all straight. See, I don't think so, Arthur, because again, this
Okay.
would flip and put that point over here, right?
That's true. Yeah. Okay. So
So,
it just flips about both the y and the x.
correct, yes. Yep,
Oh, I'm sorry. It was inverse functions that flip across the line. Y
yes.
equals x.
Inverse
Okay.
functions, yep.
Yeah.
And we
Sorry.
won't worry about inverse functions because it doesn't really help us super duper in Fourier. It is an interesting thing, but it doesn't really super duper help us.
No, I'm sorry about that. You just had to jog my memory. I
No,
forgot.
no, it's good. You can teach me something too. I love it when I learn new stuff. So just a couple things. Again, if you're trying to multiply or multiplex two functions, the product of two even functions is even. The product of two odd functions is even. The product of an even function and an odd function is odd, just like multiplying even numbers and odd numbers, it's the same thing. The sum or the difference of two even functions is even, and the sum or difference of two odd functions is odd. So that's just kind of general properties about it. So again, if you have done some Fourier series on a couple waveforms and you know they're both even or both odd, you can actually simplify. And the reason why I'm spelling this out in this level of detail is what we'll see is you're going to have to do a lot of math to calculate some of these coefficients. It's a lot of math. You'll see I've got a slide here. It's like 6 pages of slides just to do one Fourier series. But most of the time, a lot of the coefficients are zero. And if you know if it's an even or an odd function, you can actually not even have to solve for some of those coefficients. It makes things so much easier for you. So that's why I'm trying to give you a little bit of background, because if you can look at some tables, it'll actually tell you just calculate B, just calculate A, because B, the other term, the A or the B aren't going to exist because of the function type. So here is just a couple things. If it's an even function, and this may or may not be obvious, an even function almost always will have a DC offset. Why? Well, look over here. Isn't this, to replicate it, doesn't it have to be above the x-axis? You have to have a DC offset? But this is an even function. That doesn't have to have a DC offset, does it? Most of the time, they will have a DC offset, but you don't have to have a DC offset for an even function. If it's an odd function, then there is no DC offset. There's never a DC offset. And you can see that here, right? Because you have to be symmetric about the essentially the x-axis, you mirror it sort of across the x-axis. You can see how there can be no DC offset. So again, another huge time saving. If you have an even function, you may have to calculate what the DC offset is. If it's an odd function, you don't have to do any calculations for the DC offset, saving you a lot of math time to do that. So here's another one. Do I even need to do the math to show if it's an even or an odd function?
No.
Yeah, because it's x squared and x to the fourth. But I can go ahead and plug in some numbers, and I plug it in generically. If I just plug in negative x over here and do my math, right? Instead of actually plugging in 2 like we did before, 2 and negative 2, let's just plug in numbers generically. Let's plug in negative x and x. Well, if we plug in x, we get our original one. If we plug in negative x, we see that x to the fourth, we can also write it this way, right? Right? Same approach.
Yeah.
And you can see that this becomes positive 1, and that becomes positive 1, which is our original function. So f of x equals f of minus x, which means that's an even function. Okay, and then here's a plot showing what that actually looks like. Couple more, you can see even functions. We already did this one, right? You can just start drawing arrows across it. If it's an odd function, you can see over here, right? Anywhere along these lines here. Well, if I could draw that straight, sorry. 0.6 to minus 0.6, right? Or I can't go past one waveform. So here and here, those would be in opposite directions. So oftentimes it's better because you may or may not have equations. That's what gets hard. You may not necessarily have equations to actually check to see if you have x to the fourth or x cubed. Oh, and by the way, if you have an x to the fourth plus an x cubed, that automatically makes it an odd function. If you have any integer multiples, not integer multiples, any raising it to a power to an odd number, it forces it to be an odd function. But more often than not, you're going to have to be able to look at these to figure that out. So the best way to do it is pick a point, right? Up over here is what? 2.6. Let's do the same thing and go minus 2.6. They have the same point. So reading it off the curve is the most, at least to me, is the most efficient and effective way to do things. So now we're going to look at just adding a bunch of functions together. And you can see how I'm going to add the different terms and I'm going to get some different outputs. So I can sum the blue and the red. So you can see the blue is the fundamental and the red is the third harmonic. And they're basically going to have the same amplitude associated with them, but they're going to have a phase shift, right? Because we can phase shift sine and cosine waves. And so we're going to sum those and end up with these green waveforms. So you can see I've got two of them, red and blue, that are perfectly in phase with each other. What I mean by in phase is that there's no phase shift. They're both at zero. And you can see when I add those together, I get the green waveform. It kind of looks a little bit funky. And they also have the same amplitude. Over here, this amplitude for red is 1/2 the blue amplitude. And I'm going to add those together and, I'm starting to get something that looks quite a bit different than here. Now I flip-flop them. And let's see. So I've got the magnitude is 1/2, but you'll notice I also got a slight phase shift. This is starting at 0, and this is starting at 90 degrees. And the output here looks completely different than the other two. One thing to note, look at this summing here. Does that look like anything to you or closely resemble something to you? Squint your eyes really hard. What does it look like? It's starting to look like. I don't know if it looks like a cosine.
Looks a lot like a triangle wave.
Yeah, doesn't that start to look like a triangle wave?
So you just start adding more and more of those harmonic signs.
Exactly. So if I start adding a sine wave and a phase shifted sine wave, just two, that's all it is, just two of them. It's starting to look more like a triangular wave. And there's no way any of you, when you walked into class today, said, hey, I'm going to go ahead and recreate a triangular wave by adding a couple sine waves together. But you'll see by the end of our material on Fourier, we can get exact sine waves. If we allow more harmonics to be added in, eventually it's going to be a perfect sine wave. And the reason why we got to do this, again, to analyze a system that has a sine wave, how do you do it, right? L d I dt, C dv dt, yeah, you can take derivatives of that, but that gets things very, very complicated. If we go ahead and say, well, let's take a look at the fundamental and the third, and the fundamental is twice the power, maybe we can not even worry about the third because it's going to have quite a bit less power in it than the fundamental. And what we'll start to see is sometimes they jump up. Most of the time they actually decrease the amplitude, but in some cases they actually will go up. In power systems, it's particularly important, something called the triplets. So third harmonics are pretty small, but they all travel through the neutral and they can have a huge impact. This is probably 15 years ago on campus, but the transformer at the top of campus burned because everybody was using switching power supplies in the computer and the neutral wasn't rated to carry the amount of current because of the harmonics. And so it overheated and caught fire.
Ooh,
Now they use things called K-rated transformers. Have those of you worked in industry ever seen K-rated? Yeah, it's basically you have more insulation on the neutral, so it has a higher voltage rate insulation for today's systems, which have tons and tons of harmonics in them. All right. That's all I wanted to cover for today. Since you'll be going on a nice extended break here, and I don't want to start covering new trig, new Fourier stuff. I'll put a class up for next week where we'll get into more detail on these, but I wanted to give you enough, more of a motivation with a little bit of background on the other side. Any questions? Yes, ma'am.
We post it, we watch on our own, it's not gonna be like a Zoom lecture, we don't know why.
I don't know yet. It depends on, so I'm gonna create a video at some point in the next day or two that will have it pre-recorded. If I don't have access to where it's a quiet place and I can do it, in person live, then I'll just make that video available. If that would be preferred, it just depends on the circumstances of where we're at. That would be the only hardship that we have.
what about our, so the lab coming up this week is kind of like a recitation period, is that correct?
Yep. Yeah,
Okay.
I guess I talked to Mark and Mark said there were enough people who were interested in doing practice problems.
Okay,
So I asked him, I said, if you get enough interest, then go ahead and do practice problems. But if people are like, I'm going home early for break or whatever, and you're not going to have anybody there, then you can go ahead and not have labs. So I
okay.
totally left it up to him. And I guess he surveyed enough of you all that you said you wanted to do something in person.
Do we have any more actual labs for this class?
I don't think so, because when we get
Okay.
back from break, we have an exam, right?
Yeah, okay, I was just wondering, because he did open up the last lab and I did the pre-lab, but then he's like, oh, we might not have it. I'm like, oh, okay.
I thought we were supposed to do that one last week, but I could be wrong. So I'll just have
Yeah.
to double check and see. But yeah. You did do it or you didn't?
I don't know which one.
It was supposed to be Laplace circuit analysis was supposed to be the last lab that I had asked him to do. So,
I think, yeah.
okay. So I'm not sure what the next lab is. I'd have to take a look. He might have posted something trying to get the jump on me, but that's fine. Okay. Any questions? Feeling good? Feeling okay? Big plans for the weekend? Go ahead, Arthur.
I was gonna say, I feel better about this now than I did last, semester with the Fourier series, so thank you.
Oh, you're welcome. Yeah, it can be a very complicated topic, but I try to break it down into usable. Like I love the touch tone phone one, even though it's not super applicable to today. I mean, enough people have seen it that it's still a fun thing to do. And sometimes
It
it's nice
makes
to get
sense.
history. What's that?
It also makes sense.
Yeah, I agree. On the final, it'll be very basic if I do it. Very simple and basic if I do. It just depends. Definitely not exam 3. Nothing for exam 3 and 4 years.
Exam 3 is the thing. Up to flat 5.
Yes.
Or
Yep. Something else, Henry, or just give me the smile and thumbs up.
Yes, my power.
All right, folks. Have a wonderful day. Be thinking of me when I have to drive to Massachusetts Saturday morning at 3 a.m. with my son to go to a soccer thing. So
Oh, well, at 3 a.m. is better than 3 in the afternoon, I think.
that is true. There's no traffic.
Yeah.
Hopefully there's no traffic at that
Right.
hour.
Right. But drive safe.
What's that, Arthur?
But drive safe.
Yes.
Yes.
All right, everybody. Have a great day.
All
Talk
right,
to you later.
thanks.
Bye.
Have a good one.
Thank you.